Right now, a spacecraft launched in 1977 is picking up a signal from a region of space no human instrument was ever designed to hear. Not a signal it sent, a signal it received. A faint, continuous hum rising out of the empty dark between the stars. No spacecraft has ever operated this far from Earth. No instrument sent to study interstellar space has functioned this long, this far out, this close to the edge of its own power supply. This is not static. It is not noise. It is the sound of the space between stars, and NASA has confirmed it. Stay with me, because what this signal reveals about the region just outside our solar system is still being argued over by scientists today. If you're new here, this channel breaks down real space missions with real data, no filler. So subscribe if that's your thing, it costs nothing. Let us go back to the beginning. To understand why a 49-year-old spacecraft picking up a hum in the dark counts as a confirmed discovery, you have to understand what Voyager 1 was actually built to find. Launched on September 5th, 1977, on what was budgeted as a 4-year tour of Jupiter and Saturn, Voyager 1 carried 10 scientific instruments, a 12-foot dish antenna, and 3 nuclear batteries fueled by decaying plutonium, producing about 470 watts at launch, enough to run a couple of hairdryers for a mission nobody expected to outlive the 1980s. The real long-term prize, though, was never just the 2 planets. It was the edge of the sun's influence. Scientists had built a solid, well-tested model of the solar system as a kind of bubble called the heliosphere, inflated outward by the constant pressure of the solar wind, the stream of charged particles boiling off the sun in every direction. That model wasn't a guess. It came from decades of solar wind measurements, and it made a specific, falsifiable prediction. Somewhere far past the orbit of Pluto, that bubble should end, in interstellar space, the near-empty region between stars, filled with faint plasma left behind by ancient supernovae, should begin. The predicted signature of that crossing was equally specific. Inside the heliosphere, plasma density measures around 0.002 of a particle per cubic centimeter, essentially nothing. Cross into true interstellar space, and the model said that density should jump roughly 50-fold to somewhere near 1/10 of a particle per cubic centimeter. Hold on to that number, 0.1 particles per cubic centimeter, because everything Voyager later heard gets measured against it. None of this was Voyager's original assignment. NASA had originally proposed a far more ambitious grand tour, using a rare planetary alignment to visit all 4 outer giants, with a small fleet of probes, before budget cuts scaled the plan down to 2 spacecraft and 2 planets. Pioneer 10 and Pioneer 11, launched a few years earlier, had already given scientists a first rough sketch of the outer solar system, but neither carried instruments sensitive enough to properly characterize the boundary everyone suspected was out there. Voyager 1 and its twin, Voyager 2, launched 16 days apart in September 1977. Inherited that unfinished question almost by accident. A bonus objective tacked onto a mission that was never funded with the heliopause specifically in mind. That matters, because it means nobody who designed Voyager's instruments in the early 1970s was optimizing for a 50-year interstellar mission. They were optimizing for 2 flybys and a 5-year budget cycle. Everything that came after was borrowed time, running on hardware nobody built with this exact job in mind. There was one serious problem standing between that prediction and any way to confirm it. Voyager 1's dedicated plasma sensor, the instrument specifically designed to measure particle density directly, had already failed years earlier, not long after the Saturn flyby in 1980. So when Voyager crossed the termination shock, the inner edge of the heliosphere, in December 2004 and kept climbing outward for 8 more years, scientists had no direct way to confirm the moment it finally broke through. On August 25, 2012, at a distance of about 121 astronomical units from the Sun, the data shifted sharply. The steady flow of solar particles Voyager had tracked for decades all but disappeared, and cosmic rays from deep in the galaxy spiked. Every indirect sign pointed to a crossing. But the magnetic field data refused to cooperate. By the models, the field direction should have visibly shifted at the boundary, and for months it barely moved at all, leaving scientists arguing over whether Voyager had actually left home or was sitting in some unmapped transitional layer nobody had modeled. The oscillation frequency corresponded to an electron density of about 0.08 particles per cubic centimeter, almost exactly the interstellar value the models had predicted, delivered not by a direct sensor, but by a spacecraft, accidentally eavesdropping on its own surroundings after being hit by a wave that left the Sun over a year earlier. Translate that density into something you can picture. 1/10 of a particle scattered through a space the size of a sugar cube is still a near total vacuum by any human standard, thinner and colder than the best laboratory vacuums ever built on Earth, but compared to the near nothing of the heliosphere Voyager had just left, it was the difference between an empty room and one with a handful of people scattered quietly through it. Not crowded, but no longer silent. Here's where it gets genuinely strange. The 2013 detection depended entirely on luck, a solar shockwave happening to hit the right patch of plasma at the right time, arriving roughly 400 days after leaving the sun. After that single event, scientists assumed they'd be stuck waiting years for another usable reading, catching glimpses of the interstellar medium only whenever the sun happened to cooperate again. But when researchers went back through Voyager's plasma wave data collected from 2017 onward, led by Cornell astronomer Stella Ocker, they found something that had no business being there. A faint, narrow, continuously present emission, humming steadily through reading after reading, with no solar shockwave anywhere near it. Not a one-time event triggered by an accident of space weather. A signal that simply kept arriving. Published in Nature Astronomy in May 2021, the finding meant Voyager could now track the density of interstellar space continuously, sampling roughly every hundredth of an astronomical unit, an almost absurd level of precision for a measurement being taken 10 billion miles from the nearest engineer, instead of waiting for the sun to send an occasional fortunate favor. And once that continuous channel opened up, the readings themselves stopped looking simple. Rather than a flat, uniform density stretching evenly through interstellar space, the data traced out real structure. Small, astronomical unit scale fluctuations that researchers describe as turbulence threaded through a broader density trend that appeared to climb the farther out Voyager traveled. Here's the delayed reveal worth sitting with. A truly empty, featureless void does not hum in a structured, continuously present pattern, and it does not get measurably denser the deeper into it you travel for no clear reason. Something out there was shaping that signal, layer by layer, and as of the paper's own publication, the researchers had narrowed down the plausible physical causes without fully closing the case. Here's where this stops being abstract. Every particle of that plasma Voyager is now continuously listening to sits directly between us and the unfiltered radiation of the rest of the galaxy. And the heliosphere it just measured the edge of is the same bubble that has been shielding every human being who has ever lived from the full blast of galactic cosmic rays. Understanding how dense, how turbulent, and how structured that boundary and the space beyond it actually are isn't trivia for a science documentary, so it's a direct input into every serious plan for sending astronauts past the protection of the sun's magnetic field and into every calculation of how much of that radiation reaches Earth's own neighborhood in the first place. Voyager isn't listening to an abstract signal from an abstract void. It is mapping the outer wall of the only shield our species has ever had, one faint hum at a time. Space agencies planning crewed missions beyond low Earth orbit already factor radiation exposure into every design decision, from spacecraft shielding to mission duration. Limits and the boundary conditions for those calculations trace back, in part, to exactly this kind of in situ measurement. Not a satellite orbiting safely within the bubble, but a lone probe standing directly at the edge of it, reporting back what it actually finds there rather than what a model predicts it should. But almost none of that data would exist at all if Voyager itself hadn't nearly gone silent for good. In November 2023, engineers at JPL noticed something had gone deeply wrong. Voyager 1 was still transmitting, the carrier signal was there, steady and strong, but the actual content, the engineering telemetry meant to report the health of every system on board, had turned into an unreadable repeating pattern of ones and zeros. Not silence. Something worse. A machine speaking in a language nobody could parse. For a spacecraft this far out, every single command sent to investigate the problem takes roughly 22 and a half hours to arrive, and any response takes the same again to come back. A full day and a half of dead air between every guess and every answer. There is no repair truck. There is no backup unit sitting in a warehouse. There is only a small group of engineers, most of them not yet born when Voyager launched, working from decades-old documentation and ground-based hardware replicas, trying to diagnose a 46-year-old computer that could no longer accurately describe its own condition. For weeks, the team didn't even know whether the fault was software or hardware, whether it was recoverable at all, or whether Voyager 1, after 46 years, 2 planetary tours, and a journey no other machine had ever completed, had simply reached the end of its ability to speak. Every plausible fix had to be tested first on a functioning ground replica before anyone dared risk sending it to the real spacecraft, because a wrong command sent across a day and a half of silence isn't just a wasted attempt. It's a wasted attempt. You won't even know failed until the following day. Over months of painstaking, blind troubleshooting, a command sent, a day and a half of waiting, a fragment of a response analyzed, a new command drafted, the team eventually traced the fault to the flight data system, the onboard computer, responsible for packaging science and engineering data before transmission. Specifically, they zeroed in on a single corrupted chip inside that computer's memory, storing a small piece of code essential to formatting the data correctly. Think about what that actually means. A single physical component, unreachable by any human hand, 24 billion kilometers away, silently breaking the language the entire spacecraft used to speak to Earth. They couldn't replace it. They couldn't even be fully certain, at first, which chip had failed, because the system meant to report its own failures was the very system malfunctioning. So the engineers did something that sounds almost too elegant to be real. They rewrote the affected code and split it into smaller pieces, distributing those pieces across other sections of memory on the same computer that were still functioning correctly, reprogramming a dying machine's own brain remotely, one careful 18-hour transmission at a time, with no ability to undo a mistake quickly if something went wrong. In April 2024, after roughly 5 months of garbled silence, Voyager 1 sent back coherent engineering data again. And then, just months later, in October 2024, a second crisis. After engineers activated a heater on the spacecraft, an automatic fault protection system tripped and shut down Voyager's primary radio transmitter entirely, forcing a fallback to a backup transmitter that hadn't been used since 1981, carrying a signal so faint it was barely audible against the deep space background. It took the team into mid-November to fully restore normal communication. Twice in 1 year, a machine older than most of the people keeping it alive nearly stopped talking to Earth for good. Twice, it didn't. Both times, the fix came down to the same unglamorous combination: patience measured in days rather than minutes, and a willingness to trust decades-old engineering documentation over instinct. Here is what is happening right now in 2026. Voyager 1's 3 nuclear batteries are losing roughly 4 watts of power every year, a slow and completely irreversible bleed, since the plutonium inside them decays on its own fixed physical clock, no matter what anyone on Earth does. What began as 470 watts at launch has fallen to a fraction of that today. Of the original 10 scientific instruments, only a handful remain functional at all, and the mission team has had to make an increasingly brutal series of choices about which ones survive. On February 27, 2026, during a routine maneuver, the spacecraft's power levels dropped unexpectedly, coming dangerously close to triggering an automatic protective shutdown that would have forced engineers into another lengthy, risky recovery process. Rather than let that failure happen on its own terms, the team acted first. On April 17, 2026, they sent the command to permanently power down the low-energy charged particles instrument, the same detector, that had helped confirm the 2012 heliopause crossing in the first place, leaving Voyager 1 with exactly 2 working science instruments: the plasma wave system, that is still, right now, receiving that continuous interstellar hum, and a magnetometer, tracking the shape of the surrounding magnetic field. 2 instruments. Out of 10, 49 years in, still listening, according to the mission's own project managers, to a region of space no other human-made object has ever reached. Power isn't the only thing failing quietly. Some of the thrusters Voyager 1 relies on to keep its antenna precisely pointed at Earth have developed clogging problems in their fuel lines, a slow degradation with no way to repair it remotely. Suzanne Dodd has been blunt about what that means going forward. The spacecraft no longer has a backup system for its attitude control, and, in her own words, everything on board at this point is single string, meaning there is exactly one working path left for nearly every critical function, with no redundant system waiting to take over if it fails. Think about what that means for a spacecraft this far from any possible rescue. There is no second chance built into the hardware anymore. There is only whatever is still working for as long as it keeps working. The team's next move is something they've nicknamed only half-jokingly the Big Bang, a single coordinated swap of several power-hungry components for lower power alternatives executed all at once rather than gradually, in the hope of buying each spacecraft years rather than months. It was tested first on Voyager 2, the slightly less power-starved twin, in May and June of 2026. If that test succeeds, the same procedure is planned for Voyager 1 no earlier than this July, meaning that as this video reaches you, engineers may be in the process of performing a kind of open-heart surgery on a computer 25 billion kilometers from the nearest operating room, with a 2-day delay between every incision and every confirmation the patient survived it. And in a matter of months, something happens that carries no ambiguity at all. No room for debate, no dependence on luck or shock waves, just distance and the fixed speed of light. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific Standard Time, Voyager 1 will be exactly 16,094,799,96 miles from Earth. A full light day away, the distance a beam of light itself travels in 24 uninterrupted hours. Suzanne Dodd, the Voyager project manager at JPL, has described what that will mean in practice. If she sends a command and says, "Good morning, Voyager," at 8 in the morning on a Monday, she will not hear the spacecraft's answer until 8 in the morning on Wednesday. Every future exchange with this machine, from that date forward, will carry a minimum 2-day round trip built into it. Not because anything has failed, but because that is now simply the geometry of the conversation. Now, the part that doesn't resolve neatly, because it genuinely hasn't resolved in the scientific literature itself. What exactly is producing that persistent hum Voyager has been continuously receiving since 2017 is still not fully settled. The 2021 Nature Astronomy paper that first identified it lays out competing explanations rather than one confirmed cause. It could be thermally excited plasma oscillations, small, naturally occurring vibrations that arise in any warm plasma even without a dramatic external trigger. Or it could be a form of quasi-thermal noise, a broader statistical hiss produced by the constant collective jostling of charged particles drifting through the local interstellar medium. Both explanations are physically reasonable. Neither has been conclusively ruled in or out, and the researchers themselves were explicit that fully resolving it would likely require either new data from Voyager itself or an entirely new interstellar mission built to check the work. What most people are not seeing when this story gets simplified into a headline is that we don't fully know yet isn't a failure of the science. It's the honest current state of a measurement being made in a place no other instrument has ever operated long enough to verify. Step back from the plasma readings and the power budgets for a second, and there's a larger pattern worth sitting with here. Voyager 1 was never designed to still be receiving anything meaningful in 2026. It was built to survive a 4-year tour of 2 planets, using engineering standards from before the personal computer existed, using memory measured in kilobytes, using a transmitter that engineers now have to coax back to life like an aging relative, carefully, patiently, aware that one wrong move could end the conversation for good. And yet it is that same deteriorating, power-starved machine that keeps handing scientists genuinely new physics. A boundary crossing confirmed by cosmic accident, a persistent interstellar signal nobody predicted, a density gradient still not perfectly explained by the models built to describe it. This is the pattern underneath nearly every real leap in how humanity understands its place in the universe. Not a single triumphant discovery arriving on schedule, but old instruments, pushed decades past their intended lifespans, receiving signals nobody built them expecting to catch, forcing the models to catch up to the machine instead of the other way around. Consider, too, that every mission NASA plans today gets budgeted and reviewed against an expected lifespan. And Voyager stands as the permanent, uncomfortable reminder that the most important thing a spacecraft ever hears might not arrive until decades after everyone who designed its instruments has retired or died, waiting on a discovery nobody wrote into the original proposal. Stella Ocker wasn't yet born when the plasma wave instrument she used launched into space. That's not a footnote. That is, quite literally, how this kind of listening works. One generation builds the ear, and a much later generation finally learns what it's been hearing all along. And there's a harder truth underneath that, one worth naming plainly. The reason anyone can still hear anything at all is that a small team of engineers has spent decades treating a piece of 1970s hardware with the same patience most institutions reserve for something new and expensive. Every watt has been fought for. Every instrument shutdown has been argued over, sequenced, and delayed as long as physically possible. That kind of institutional patience is rare, and it is not guaranteed to outlast the spacecraft itself. There is a story engineers at JPL tell about talking to Voyager 1 now, and it isn't really about data at all. It's about the wait. Every command goes out into the dark and simply disappears for the better part of 2 days, with no way to know, in that gap, whether the machine on the other end is still there to receive it. And somewhere in that same silence, riding along a channel nobody designed to be poetic, is a continuous, faint signal that has been arriving since 2017. Not sent by anyone, not aimed at anyone, just the sound of the space between the stars, picked up by an antenna built during the Ford administration, and still, somehow, pointed the right way. Voyager 1 gave up its eyes back in 1990, when its cameras were switched off for good after one last photograph of home. The ground software that once processed those images, long since deleted, to save what little memory remained. It kept its ears. Bolted to its side, a gold-plated record still carries greetings in 55 languages, a map showing the way back to Earth, and a diagram of the hydrogen atom meant to explain, to whoever might one day find it, roughly when and where it was made. Nobody expects it to be found. It travels anyway. And what Voyager has heard in the decades since is a universe that does not go quiet just because there is no one out there to listen. A hum in the dark, still arriving 1 full day late, for as long as this small, aging spacecraft has enough power left to keep receiving it. So here's everything in one breath. Voyager 1 launched in 1977, crossed into interstellar space in 2012, and had that crossing confirmed a year later only because a lucky solar shockwave rang the surrounding plasma like a bell. In 2021, scientists discovered something nobody predicted. A continuous, unexplained plasma signal Voyager has been receiving from deep interstellar space since 2017, letting them track the density of that region in real time for the first time ever. A catastrophic computer failure nearly silenced the spacecraft in 2023 and 2024, fixed only by engineers rewriting its memory one careful, day-and-a-half delayed command at a time. Today, in 2026, just 2 of Voyager's original 10 instruments still function. Power keeps bleeding away at 4 watts a year, and this November the spacecraft crosses the 1 light day mark, permanently doubling the weight on every future exchange with Earth. And the exact source of that interstellar hum it's still receiving, right now, remains genuinely unresolved. If any part of this made you want to know what happens next, whether the Big Bang power swap keeps Voyager 1 alive past this July, or whether this is the beginning of its final silence, hit subscribe and turn on notifications, because I'll be covering that outcome the moment NASA confirms it. One question before you go: would you rather see NASA pour its remaining resources into keeping this 50-year-old machine alive a few more years, or let it go quiet and put everything into building something new to take its place? Let me know in the comments. I read every single one.